Hello, we are Group 15. I'm Hayden.
And I'm Melanie, and we did our analysis on the basketball hoop.
Our goal of this project is to determine the failure limit of a basketball rim. The tested basketball hoop is made of aluminum and tested with a safety factor of 1.5. Once a force is applied on the rim, if the hoop experiences a stress of over 35,000 psi, it is considered a failure. We will be testing the rim with varying cross-sectional diameters to see where the failure point is.
We have a picture here just showing the standard basketball hoop that we'll be using with the height of 10 feet, diameter of 18 inches, and the backboard is 6 feet by 4 feet. We are going to be testing the force of a basketball player dunking on the rim, specifically the MSU basketball team. For this team, the weight range is from 185 to 250, and we have a clip here to show you what we will be analyzing.
The backboard used was originally constructed in NX and then brought into ANSYS. The pole and the rim were modeled in ANSYS as beams. A fixed support was applied at the bottom of the pole, and a force is applied on the rim.
The initial mesh generated, as you can see, the two meshes did not match up because we were using two different geometries, the plate and the beam. To fix this, we had to have the element sizes be the same, so we needed to add a refinement to the beam and then also create two connections, one between the backboard and the rim and the second one between the post and the backboard bars.
The picture on the left is from the previous slide, where we created connections and refined the beam. In order to obtain accurate results, we chose to change the relevance from coarse to medium. You can see the number of nodes and elements at the bottom to compare the two relevances.
These two graphs are showing the result from the diameter of the rim change from 0.75 inches to 1.5 inches. This is the range that we decided would be a good estimate of a rim in real life. And on the stress graph, we included a red line to show the yield strength of aluminum. And as you can see, the point at the 1.5 rim diameter gave us the best results because it is below the yield point, but also includes our safety factor of 1.5.
For the deflection results, as the rim diameter increased, the experienced rim deflection decreased. This trend was closer to linear than the stress pattern. The two figures below show the stress results of the smallest diameter rim and the largest diameter rim. The top figure is the smallest diameter rim, and the bottom figure is the largest diameter rim. It is clear from these pictures that the smaller diameter rim experienced much more deflection than the larger, and experienced much more stress. It can be concluded from these images that the 1.5 or larger diameter rim is the more optimal size.
Here we are comparing aluminum versus steel on the rim material. They are both applied with the same force of the 250 pounds, and we wanted to show the different stress that happened between them. There actually was not much change. The steel was a little bit less, and we think that there was not as big of a difference because the only material that we ended up changing was the rim, and the rest of the basketball hoop was still aluminum. So this might have not as large of an effect as expected.
The figures below show the results from the 1.5-inch diameter rim, which we concluded was the best diameter. The picture on the right shows the deformation of the rim. As the rim became larger, the deformation was less because more force is transferred to the backboard and the side supports. We concluded that the 1.5-inch diameter rim is the best because it had the least amount of stress.
We wanted to identify certain uncertainties and simplifications that we made through our analysis. We analyzed a standing hoop, but in a real MSU game, it has multiple supports and is not just a standing hoop. We also simplified the geometry. The rim of a basketball hoop is not just a single circle. It has some other layers as well to it, and the materials of the basketball hoops usually involve more than just a uniform metal throughout. And the way that we had placed the force, it would be applied not to the entire face of the rim, as we did in the analysis, but just where the hands of the basketball player are touching.
Thanks.